Welcome to Server Logic Simplified.
Have you ever needed to confirm a crucial piece of information, like an inventory count or a financial balance, only to find that the number unexpectedly changed right when you looked a second time? It is a bit like reading a report and seeing different figures for the same item within moments. This phenomenon, especially within database systems, can lead to serious headaches. In database terminology, this annoying situation is called a non-repeatable read, and it is problematic because it fundamentally undermines the consistency and reliability of your data. When a transaction experiences a non-repeatable read, it means that during its execution, if it attempts to read the same row of data multiple times, it might retrieve different values on each read. This violates the core expectation that a transaction operates on a consistent snapshot of the data. The underlying mechanism for non-repeatable reads is concurrent database access without sufficient isolation. Let us unpack that. Imagine transaction A begins, reads a specific record, say an account balance of $1,000. At the same time or shortly after, another operation, transaction B, modifies that very same account balance, perhaps depositing to $100, and then commits its changes. Now, if transaction A, still running, attempts to read that exact same account balance again, it will retrieve $1,000 to $100. Transaction A has seen the same data item change within its own boundaries. This is highly problematic because any logic within transaction A that depends on the initial read will now be operating on stale or inconsistent information. For instance, if transaction A was calculating a total based on the $1,000 balance and then attempted to debit an amount, the later read of $1,000 to $100 would completely invalidate its prior calculation, potentially leading to incorrect deductions or overspending. This scenario highlights how non-repeatable reads can cause financial inaccuracies, inventory discrepancies, and faulty business decisions. They manifest acutely in database isolation levels like read committed, where a transaction is only guaranteed to see committed changes, but not necessarily a stable view of all data it accesses repeatedly. This can result in applications making decisions based on incomplete or shifting realities, leading to a cascade of errors throughout a system. To avoid the pitfalls of non-repeatable reads, developers often configure their database transactions to operate at higher isolation levels. The repeatable read isolation level is specifically designed to prevent this issue. When a transaction runs at the repeatable read level, the database ensures that any row read by that transaction will maintain its initial value for the entire duration of the transaction, even if other concurrent transactions modify or commit changes to those rows. The serializable isolation level also prevents non-repeatable reads, offering even stronger consistency by also guarding against phantom reads. The choice of isolation level involves a trade-off between data consistency and concurrency performance, as higher isolation levels typically involve more locking or resource overhead. Understanding this interaction between concurrent operations and isolation levels is crucial for building robust applications. This concept is foundational to achieving what is known as transactional integrity, ensuring that database operations are reliable and maintain data accuracy even under heavy load. Modern database systems often use mechanisms like multi-version concurrency control, or MVCC, to achieve repeatable reads without always relying on extensive locking. MVCC allows a transaction to read an older, consistent version of a row while other transactions are modifying the current version. This provides the desired isolation without blocking concurrent write operations as much. Ultimately, properly addressing non-repeatable reads through careful selection of transaction isolation levels is paramount for any application that relies on data accuracy. It means your reports will reflect truthful figures, your financial transactions will be sound, and your business logic will execute on a consistent reality. By ensuring that transactions have a stable and reliable view of the data they interact with, you uphold the trust users place in your system and prevent the subtle data anomalies that can lead to significant problems down the line.
If this helps you code smarter, like, subscribe, and stay tuned for more.